Yo. All right. Today we're going to talk about this cool concept called differentiability, right? We've talked about continuity before, and differentiability and continuity are pretty related, right? But as you probably guessed, differentiability deals with derivatives, right? We're also going to introduce a new type of limit. Sorry. It's not super bad, and we're not really going to do a ton of work with it. Just kind of going to introduce you to it, and I'll maybe release probably one of those community posts about me doing the work on one of those, right? So let's begin, right? Differentiability, and I'll write this down here, actually. Differentiability. Differentiability is, you can take the derivative of a function at a point. So, in other words, the derivative exists. And I'll just write like kind of blank space there because you can have an entire function that's differentiable. You can have a single point that's differentiable. You can have a single point that's not differentiable, right? And that's kind of the big thing we'll be discussing because those single points or intervals that are not differentiable cause problems sometimes. Because if something's not differentiable, its derivative doesn't exist. Then we get into some wacky stuff, right? So I'll kind of show you what happens and how to spot these and how to deal with them, right? So draw out a graph over here. I'll need all 4 quadrants today, right? Kind of a goofy looking graph, but the most common way you'll see differentiability addressed, I think, is with the absolute value function. It's going to be the example we use today. So I'm just going to say this is like f of x, right? Like f of x equals absolute value of x, right? That function looks just about like this. Linear line, except all the negative parts are flipped. This part here in quadrant 3, boom, up to quadrant 2, right? All positive. And so you get to this point, this is where limits come in, right? Because I'll use red, right? What happens as you approach this point? Because we know we could take the derivative of like this part over here, this part over here. It's just a straight line. It'd just be a constant, right? These areas here. But you get to this point at x equals 0, right? Now really think about what your derivative is doing. Not just what your function's doing. Your function's approaching 0, right? I can look at this graph right now and tell you that this is a continuous graph everywhere, even at this point x equals 0. But it's not differentiable at x equals 0. And why isn't it? So if this is just the function value, absolute value of x, right? You could write that as a piecewise function, but I'm not going to right now. Just think about this. This line is basically y equals negative x, right? Over here, it's y equals negative x, right? This is where you kind of get into the piecewise part. And this part, it's y equals x, right? And those will have domain restrictions on them involving that x equals 0 part. Now, think about what your derivative is doing. Right here, it's negative 1 on this side of the graph. Right here, where it's increasing, well, they're increasing, but whatever. It's positive 1, right? On this side of the graph. So as we approach 0, we have a derivative of positive 1. So I just kind of drew a tangent line, like a little magic tangent line finder, like we have here in my calculator cover. On this side of the function, it's just a straight line, right? That's our tangent line. But on this side of the function, it's also a straight line, but it's in the opposite direction, perpendicular, right? So what happens? You don't have a tangent line that looks like this. You do not. Don't have one that looks like that, and we'll talk more about that later. But you don't have a tangent line because your derivative doesn't exist at that point. You have conflicting derivatives that at that instantaneous point don't cancel out. There's no turn, right? But if we have a function such as, right, like I'll just draw a parabola real quick, similar to the one we used in our last video, right? Our derivative here exists everywhere, even at this peak. It is x equals, right? It is going to have a derivative equal to 0, right? Indicating a horizontal tangent line, right? But then this one doesn't. It's really because of that sharp curve. You instantaneously go from a derivative of negative 1 on this quadrant 2 side to instant derivative of positive 1 here on the quadrant 1 side, right? Instantly. There's no area where it smoothly changes. But here on this graph, it does. As you increase and increase, your derivative slowly changes, right? And there's no sharp motion. And really that sharp motion is going to create discontinuity, or not discontinuities, areas where the function is not differentiable, right? So, kind of erase all this junk here. Let's talk about how we find it. Now we're going to introduce this new limit. Might not like it, but I think it's pretty cool, right? Pay attention to this. This is important. F prime of, I'm going to use A. A is going to be a number, something you plug in. F prime of A, not F of A. This is going to equal the limit as x approaches A of f of x, not f prime of x, f of x, minus f of A over x minus A, right? Prime here, not prime over there. So if you look at this and you think about what this does, and I'll tell you right now, because it's really, explaining this is complicated. And I'll probably do some sort of like proof on that on like a community post later. This makes little to no sense if you just think about it. But I'm going to tell you, this skips the derivative and just finds the value of the derivative at a point, right? You skip the whole doing the power rule or limit definition of a derivative, you can just go straight to the slope value, right? So this, you're gonna have an f prime value on this side, but then everything over here is just going to be f of x, right? And then on this left side here, you've got f prime and then of A. Right. And so this limit specifically is going to allow us to address differentiability. Because if this limit doesn't exist, remember this limit finds the value of the derivative at x equals A. If this doesn't exist, there's no derivative there. It's not differentiable. But if it does exist, there is a derivative there. It is differentiable, right? And then after this, we're going to talk about other ways to spot areas where the function's not differentiable. We're going to address the similarities between continuity and differentiability. And then some other stuff. I think we'll look at this limit a bit. But let's talk first about some other ways to think about areas where your function isn't differentiable, right? So I've already mentioned sharp curves. The absolute value has a sharp point right at that x equals 0 point. But there are also some other ways your function could be not differentiable, right? First one, I talked about having a tangent line that's vertical, which is not the case for this, but sometimes you'll have a function where it is. And so I'm going to draw a function like this. That's some sort of root function. That's going to be like negative cube root of x, I think, what I just drew there. What you're going to have is you're going to have a smooth tangent line, but all of a sudden, oh, it goes straight down. You'll find that here, and I kind of poorly drew it, but this function, there is a point at x equals 0 where that function is going straight down instantaneously, right? So you're going to make a tangent line, and the tangent line would just be a vertical line at x equals 0, right? But what would the slope of that line be? The slope of a vertical line is undefined, so your derivative does not exist there. This would not exist. Okay, boom. Another one you'll see is what we call a cusp. Really, really rare. You don't see these often, but you have to know of their existence because if you're going to like engineering, you'll see models and things that are modeled with cusps. Cusps look like this. Very similar to the absolute value function, except it's kind of a curved motion into a sharp point, right? Curved motion into a sharp point. So be aware of that. Don't really worry about it too much. I probably won't go over it a lot in the future, but if you're going to like engineering, you'll probably see that a few times. You'll see like rational functions too, whatever. Yeah, a lot of rational functions. So the final one is, and it'll lead us into our next topic, discontinuities, right? I'll tell you right now, the derivative of this function, if I were to graph it out, because I know what this derivative looks like, it looks like this. Really, really weird. This is just something you'll probably remember, but I'll explain it real quick. The derivative of absolute value of x. I'm not going to show you how to do like the math behind that because it involves piecewise equations. It's actually not that difficult, but you see this is just a linear line. Remember, I wrote y equals x, and over here it's y equals negative x with some domain restrictions. Right of 0, it's y equals x. So the derivative of that is just equal to 1, right? This is 1, and this is negative 1. And remember, this is f prime. So this model slopes. Your slope is equal to 1. Your slope is equal to negative 1 on this side, because remember, it's decreasing. That graph is pointing down as x increases, really. You're looking at what does the y value do as the x value increases most of the time, right? But then at this point here, you have a jump discontinuity. If you remember all the way from one of our first videos, that's a jump discontinuity, right? So discontinuities will also cause points of where your function isn't differentiable, right? Sharp point or sharp curves. Now, if we were to take the double derivative or second derivative of this, you can't take the derivative at x equals 0 because there's a jump discontinuity, right? So both this function and its derivative actually have a point of indifferentiability at x equals 0, right? So that's pretty cool. Now, let's talk about how continuity and differentiability work together, really. So I'm going to erase this, but keep this equation up here because it's a pretty important limit. We won't use it a ton in the future, but it really does explain why. And because most of the time we'll just look at a function and be like, oh, that's not differentiable there, right? Okay, boom. Continuity. This is a continuous graph, right? You can draw that entire graph without moving your pen or without lifting your writing utensil, but it's not differentiable because that sharp curve, right? So here's a big kind of logic statement I will write. Continuity does not always mean differentiability. So not always, and I'll write like little not always here. And I'll just write diff. I'll abbreviate differentiability, usually from now on as diff, right? Writing differentiability is pretty lengthy. But then, however, differentiability always implies continuity. And I'll abbreviate continuity as CONT there. Always. If a function is differentiable, it is continuous, right? It is, always. And now let's get into the limit proof of that. We're going to use this limit a bit. So, remembering all the way back to one of our first, I think maybe the first videos, or the first video we made here, talking about when does a limit exist? Now we're going to use that here, right? Because if this limit doesn't exist, the derivative doesn't exist. But if it does exist, the derivative does exist. We're going to check the left and right side, right? So in order for this limit to exist, you're going to need both the limit as x approaches a from the left side of f of x minus f of a over x minus a, and the limit as x approaches a from the right side of f of x minus f of a over x minus a, right? You need these to be equal to each other. If these are equal, then this exists, right? But if they're not equal, right? Like if we, like here, we do this slope value, and you can pick out a point, but it just has to be equal. You're really testing for, is this differentiable? So you're really gonna pick an a value of 0, right? Boom, right there at the middle. So what happens to the slope, sorry for all that noise, on the left side and on the right side? On the left side here, -1. Right side here, +1. Those derivatives don't equal, right? Or my bad, those limits don't equal. If you were to take the limit of this right side, you would actually get 1, right? I'll show you that later. You would get 1 if you did that limit. And on the left side here, you would get -1. So since -1 does not equal 1, this does not exist. And so your function's not differentiable. And now, we're gonna kind of go into the next thing. There's a little one more condition if they do equal. Like let's say for a whole different function, we get the left side of that limit and the right side of that limit equal to 3. Now, what does that mean, right? Now, I'm going to erase this kind of logic statement up here. You have a function, kind of like a parabola, right? You're testing for differentiability at this point. We can look at that function and say it's differentiable everywhere, by the way. But here, as you go from the left side, your slope of that tangent line is going to be equal to 3, but then also on the right side, it's going to be equal to 3, right? So that derivative exists, right? So that's what that limit finds. But we have to address the issue of continuity, right? Think about this. For that limit to exist, remember our limit conditions? For a limit to exist, the function has to be continuous at the point we're checking, right? That goes back to our first or second video ever. It's a good review video to go back to if you want to catch up on this. So this is an important topic, right? Function has to be continuous at that point. The left limit has to equal the right limit. And then the final condition is that your limit output value has to equal the function output value, right? So let's go back to this one. Let's say that this here, oh my bad, for continuity, yes. For continuity, your, I'm just gonna say this is g of x. Sorry, I'm getting kind of messy and unorganized here, but g of x, g of, or I guess, a, right? Let's just use a. G of a must equal the limit as x approaches a, right? From both sides of g of x, right? So that's our condition for continuity, right? That limit must exist. The function value must exist, and the function value must equal the limit value. Same thing with derivatives here. You have to be continuous. Your left limit has to equal the right limit. Your function has to actually exist there, because remember, at a discontinuity, so at a removable discontinuity, your function doesn't exist, not differentiable, right? And then left limit has to equal right limit. Okay. So again, I'll probably release a community post, little piece of paper explaining why this works. We'll work out one of those limits. But we're really not going to do any super intense examples with this. If you ever see in a kind of textbook, they'll give you usually a graph or function you can explain pretty well, right? But before we wrap this up, let's go back to this function, because this is one of my favorite functions ever, right? The derivative of the absolute value of x. It's actually written as the absolute value of x over x, right? Further down the line, don't need to worry about that right now, right? But then if you look at the limit, if you go as x approaches 0, as you approach from the right side, you're approaching -1. So from the right side, and I'm not going to write all that out, that's equal to 1. But from the left side, right, equals -1. So now what does this tell us? You can do the whole f prime of a. You could do that f prime of a limit, right? Remember that one that I just showed you? Or you could just do a normal limit of the derivative. Kind of interesting. You can either take the, I'll kind of write this, and that's equal to the limit. Probably shouldn't have erased that, as x approaches a of f of x minus f of a over x minus a. And that'll address differentiability. Or you can have the derivative, and you could just do a normal left and right-sided limit. So depending on what you're given, what information you're given in a situation, if you're given a function, you're going to use the derivative limit equation. If you're given the derivative, you want to find out if it's differentiable. 1, look. 2, you can use a normal limit, right? You can use a normal limit to prove that, right? So find it interesting that functions and their derivatives are related through different kinds of limits in a similar proof, right? If you're differentiable, you have to be continuous. But if you're continuous, doesn't always mean you're differentiable. It's a big takeaway of this, right? Remember that. And this fancy new limit really is derived from how we can use normal limits. So remember, there are always multiple ways to go through these types of problems, right? Anyway, hope you learned something today. Sorry for kind of being stuttery and kind of winging it today. I didn't really have time to make up a huge script, but it's whatever. I think I still got the point across. This limit, these normal limits that we addressed in our first or second video, continuity does not equal differentiability, but differentiability equals continuity. That's really all I have to say today. Goodbye, class.